Classification of elements and periodicity in properties. The periodic table is arguably the most important concept in chemistry, both in principle and in practice. It is the everyday support for students. It suggests new avenues of research to professionals and it provides a succinct organization of the whole of chemistry. It is a remarkable demonstration of the fact that the chemical elements are not a random cluster of entities, but instead display trends and lie together in families. An awareness of the periodic table is essential to anyone who wishes to disentangle the whole world and see how it is built up from the fundamental building block of the chemistry, the chemical elements. Glenn T. Seaborg. In this unit, we will study the historical development of the periodic table as it stands today and the modern periodic law. We will also learn how the periodic classification follows as a logical consequence of the electronic configuration of atoms. Finally, we shall examine some of the periodic trends in the physical and chemical properties of the elements. Why do we need to classify elements? We know by now that the elements are the basic unit of all type of matter. In 1800, only 31st elements were known. By 1865, the number of identified elements had more than doubled to 63. At present, 114 elements are known. Of them, the recently discovered elements are man-made effort to synthesize new elements are continuing. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists searched for a systematic way to organize their knowledge by classifying the elements. Not only that is would rationalize no chemical fact about element but even predict new ones for undertaking further study. Genesis of periodic classification. Classification of elements into group and development of periodic law and periodic table are the consequence of systematizing the knowledge gained by a number of scientists through their observation and experiment. The German chemist John Davender in early 1800 was the first to consider the idea of trends among properties of elements. By 1829, he noted a similarity among the physical and chemical properties of several groups of three elements triads. In each case, he noticed that the middle element of each of the triads has an atomic weight about halfway between the atomic weight of the other two. Also, the properties of the middle element were in between those of the other two members. Since Davender's relationship, referred to as the law of triads, seemed to work only for a few elements, it was dismissed as coincidence. The next reported attempt to classify elements was made by a French geologist, A.E.B. de Champs-Courtois, in 1862. He arranged the then known elements in order of increasing atomic weight and made a cylindrical table of elements to display the periodic recurrence of properties. This also did not attract much attention. The English chemist John Alexander Newland in 1865 propounded the law of octaves. He arranged the element in increasing order of the atomic weight and noted that every 8 element had properties similar to the first element. The relationship was just like every 8 note that resembles the first in octaves music. Newland's law of octaves seemed to be true only for elements up to calcium. Although his idea was not widely accepted at the time, He, for his work, was later awarded Davy Medal in 1887 by the Royal Society London. The periodic law as we know it today owes its development to the Russian chemist Dmitry Mendeleev 1834 to 1907 and the German chemist Lothar Meyer 1830 to 1895. Working independently, both the chemists in 1869 proposed that one on arranging element in the increasing order of the atomic weight, similarities appear in physical and chemical properties as at regular intervals. Lothar Meyer plotted the physical properties such as atomic volume, melting point, and boiling point against atomic weight and obtained a periodically repeated pattern. Unlike Newland's Lothar Meyer observed a change in length of that repeating pattern. By 1868, Lothar Meyer had developed a table of the elements that closely resembles the modern periodic table. However, his work was not published until after the work of Dmitry Mendeleev, the scientist who is generally credited with the development of the modern periodic table. While Dovell initiated the study of the periodic relationship, it was Mendeleev who was responsible for publishing the periodic law of the first time. It states as follows: the properties of the elements are a periodic function of their atomic weight. Mendeleev arranged elements in horizontal row and vertical column of a table in order of their increasing atomic weight in such a way that the element with similar properties occupied the same vertical column or group. Mendeleev's system of classifying elements was more elaborate than that of Lothar Meyer's. He fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formula and properties of the compound formed by the elements. He realized that some of the elements did not fit, and with his scheme of classification, if the order of atomic weight was strictly followed, he ignored the order of atomic weight, thinking that the atomic measurement might be incorrect, and placed the element with similar properties together. For example, iodine with lower atomic weight than that of tellurium group 6 was placed in group 7 along with fluorine, chlorine, bromine because of similarities in properties. At the same time, keeping his primary aim of arranging the element of similar properties in the same group, he proposed that some of the elements were still undiscovered and therefore left several gaps in the table. For example, both gallium and germanium were unknown at the time Mendeleev published his periodic table. He left the gap under aluminium and a gap under silicon and called these elements eka aluminium and eka silicon. Mendeleev predicted not only the existence of gallium and germanium but also described some of their general physical properties. These elements were discovered later. Some of the properties predicted by Mendeleev for this element and those found experimentally are listed in table 3.3. The boldness of Mendeleev's quantitative prediction and their eventual success made him and his periodic table famous. Mendeleev periodic table published in 1905 in figure 3.1. 3.3 Modern periodic law and the present form of the periodic table. We must bear in mind that when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of the 20th century. Witnessed profound development in theories about subatomic particles in 1913. The English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of the element. A plot of V, where V is frequency of X-ray emitted, against atomic number Z gave the straight line and not the plot of V versus atomic mass. He thereby showed that the atomic weight is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was therefore accordingly modified. This is known as the modern periodic law and can be stated as the physical and chemical properties of the element are periodic function of their atomic number. The periodic law revealed important analogies among the 94 naturally occurring elements. Neptunium and plutonium, like actinium and protoactinium, are also found in pitch blende and O of uranium. It stimulated renewed interest in organic chemistry and has carried into the present with the creation of artificially produced short-lived elements. You may recall that the atomic number is equal to the nuclear charge. Example, number of proton or the number of electron in a neutral atom. It is then easy to visualize the significance of quantum number and electronic configuration in periodicity of elements. In fact, it is now reorganized that the periodic law is essentially the consequence of the periodic variation in electronic configurations, which indeed determine the physical and chemical properties of element and their compound. Numerous forms of periodic table have been devised from time to time. Some form emphasize chemical reaction and valence, whereas others states the electronic configuration of elements. A modern version, the so-called long form of the periodic table of the elements, is the most convenient and widely used. The horizontal law, which Mendeleev called series, are called period and vertical column groups. Elements having similar outer electronic configuration in their atom are arranged in vertical columns referred to as group or families. According to the recommendation of International Union of Pure and Applied Chemistry IUPAC, the group are numbered from 1 to 18, replacing the older notation of group. There are altogether seven periods. The period number corresponds to the highest principal quantum number n of the elements in the period. The first period contains 2 elements. The subsequent period consists of 18, and 32 elements respectively. The 7th period is incomplete and, like the 6th period, would have a theoretical maximum. On the basis of quantum number of 32 elements in this form of the periodic table, 14 elements of both 6th and 7th period, lanthanoids and actinoids respectively, are placed in separate panels at the bottom. 3.4 Nomenclature of elements with atomic number decreasing 100. The naming of the new elements had been traditionally the privilege of the discoverer or discoverers, and the suggested name was ratified by the IUPAC. In recent years, this has led to some controversy. The new element with very high atomic number are so unstable that only minute quantities, sometimes only a few atoms of them, are obtained. Their synthesis and characterization therefore require highly highly sophisticated, costly equipment and laboratory. Such work is carried out with competitive spirit only in some laboratories in the world. Scientists, before collecting the real data on the new element at time, get tempted to claim for its discovery. For example, both American and Soviet scientists claimed credit for discovery elements 104. The Americans' name is Rutherfordium, whereas Soviet's name is Korchotovium. To avoid such problems, the IUPAC has made recommendation that until a new element's discovery is proved and its name is officially reorganized, a systematic nomenclature be derived directly from the atomic number of the elements using the numerical roots for 0 and number 1 to 9. These are shown in table 3.4. The roots are put together in order of digits which make up the atomic number, and M is added at the end. The UPSC name for element with Z above 100 are shown in figure 3.5. Thus, the new elements first get a temporary names with symbol consisting of 3 letter permanent name and symbol are given by a vote of IUPAC representative from each country. The permanent name might reflect the country or state of the country in which the element was discovered or pay tribute to a notable scientist. As of now, elements with atomic number up to 118 have been discovered. Official name of all elements have been announced by IUPAC. 3.5 Electronic configuration of element and the periodic table. In the preceding unit, we have learned that an electron in an atom is characterized by a set of 4 quantum numbers, and the principal quantum number define the main energy level known as cell. We have also studied about the filling of electron into different substances, also referred to as orbital SPDF in an atom. The distribution of electron into orbital of an atom is called its electronic configuration. An element's location is the periodic table reflect the quantum number of the last orbital field. In this section, we will observe a direct connection between the electronic configuration of the element and the long form of the periodic table. Electronic configuration in periods. The periods indicate the value of n for the outermost valence cell. In other words, successive periods in the periodic table is associated with the filling of the next higher principal energy level n is equal to 1, is equal to 2, etc. It can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. The first period n is equal to 1 start with the filling of the lowest level 1s and therefore has 2 elements hydrogen and helium. When the first cell is completed, the second period starts with lithium and the third electron enter the 2s orbital. The next element, beryllium, has 4 electrons and has the electronic configuration. Starting from the next element, boron, the 2 p orbitals are filled with electron when the L cell is completed at neon. Thus, there are 8 elements in the second period. The third period n is equal to 3 begin as sodium and the added electron entered as 3s orbital. Successive filling 3s and 3p orbital give rise to the third period of 8 elements from sodium to argon. The fourth period n is equal to 4 start as potassium and the added electron fill up the 4s orbital. Now you may note that before the 4p orbital is filling, Field filling up of 3D orbital become energetically favorable and become across the so-called 3D transition series of elements. These start from scandium, which has the electronic configuration. The 3D orbitals are filled at zinc with electronic configuration. The fourth period in at krypton with the filling of the fourth period orbital. Altogether, we have 18 elements in the fourth period. The fifth period n is equal to 5 beginning with the rubidium is similar to the fourth period and contain the 4D transition series starting at yttrium. This period end at xenon with the filling up of the 5 p orbitals. The sixth period contains 32 elements and successive electron enter 6s, 4f, 5d and 6p orbitals. In the other filling up of the 4f orbital begins with cerium and end at lutetium to give the 4f inner transition series, which is called the lanthanoid series. The seventh period is similar to the sixth period with successive filling up of the 7s, 5f, 60 and 7p orbital and include most of the man-made radioactive elements. This period will end at the element with atomic number 180, which will belong to the noble gas family. Filling up of the 5f orbital after actinium give the 5f inner transition series known as the actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. B. Group-wise electronic configuration. Elements in the same vertical column or group have similar valence shell electronic configuration, the same number of electrons in the outer orbital and similar properties. For example, the group 1 elements alkali metal all have n small valence shell electronic configuration as shown below. Thus, it can be seen that the properties of elements have periodic depends upon its atomic number and not on relative number mass. Theoretical foundation for the periodic classification. The elements in a vertical column of the periodic table constitute a group or family and exhibit similar chemical behaviors. This similarity arises because these elements have the same number and same distribution of electrons in the outermost orbital. We can classify the elements into 4 blocks, which S block, P block, D block and F block, depending on the type of atomic orbital that are being filled with electrons. This is illustrated in figure 3.3. We notice 2 exceptions to these categorizations. Strictly, helium belongs to the S block, but its positioning in the P block along with other group 18 electron elements is justified because it has a completely filled valence shell and as a result exhibit properties characteristics of other noble gases. The other exception is hydrogen. It has only one S electron and hence can be placed in group 1 alkali metals. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to a group 17 halogens family elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in figure 3.2 and figure 3.3. We will briefly discuss the salient features of the four type of element marked. 3.6 Electronic configurations and type of element SPDF block. The above will the principle and the electronic configuration of atom provide the periodic table. More about these elements will be discussed later during the description of their features. Certain terminology has been used which has been classified in section 3.7. 3.6.1 Thus block elements. The element of group 1 alkali metal and group 2 alkaline earth metal which have NS1 and NS2 outermost electronic configuration belong to the H block element. They are all reactive metal with low ionization enthalpy. They lose the outermost electron radially to form 1 plus ion or 2 plus ion. The metallic character and the reactivity increase as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S block element, with the exception of those of lithium and beryllium, are predominantly ionic. Their P block elements. The P block elements comprise those belonging to group 13 to 18, and these together with the S block elements are called the representative elements or main group elements. The outermost electronic configuration varies from NS2NP1 to NS2NP6 in each period. At the end of each period is a noble gas element with a close valence shell NS2NP6 configurations. All the orbital in the valence shell of the noble gases are completely filled by electron, and it is very difficult to alter this stable arrangement by the addition or removal of electron. The noble gases thus exhibit very low chemistry activity. Preceding the noble gas family are two chemically important groups of nonmetals. They are the halogens group 17 and the chalcogens group 16. These two groups of elements have highly negative electron gain enthalpies and rarely add 1 or 2 electrons respectively to attain the stable noble gas configuration. The non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. 3.6.3 The D block element transition elements. These are the elements of group 3 to 12 in the center of the periodic table. These are characterized by the filling of inner d orbital by electron and are therefore referred to as the D block elements. These elements have the general outer electronic configuration. They are all metals. They mostly form color ions, exhibit variable valence, paramagnetism, and often used as catalyst. However, Zn, Cd, and Hg, which have the electronic configuration, do not show most of the properties of transition elements. In a way, transition metals form a bridge between the chemically active metal of S block elements and the less active elements of group 13 and 14, and thus take their familiar name transition element. The F block elements, inner transition elements. The two rows of elements at the bottom of the periodic table called the lanthanoids Cl and actinoids Th are characterized by the outer electronic configurations. The last electron added to each element is filled in F orbital. These two or series of elements are hence called the inner transition element F block elements. They are all metals. Within each series, the properties of the elements are quite similar. The chemistry of the early actinoids is more complicated than the corresponding lanthanoids due to the large number of oxidation states possible for these actinoids elements. Actinoids elements are radioactive. Many of the actinoids elements have been made only in nanogram quantities or even less by nuclear reaction, and their chemistry is not fully studied. The elements after uranium are called transuranium elements. Three point 6.5 Metals, non-metal and metalloids. In addition to displaying the classification of elements into SPD and A block, figure 3.3 show another board classification of elements based on their properties. The elements can be divided into metal and non-metals. Metals comprise more than 78% of all known elements and appear on the left side of the periodic table. Metals are usually solid at room temperature. Mercury is an exception. Gallium and caesium also have very low melting points. Metals usually have high melting and boiling points. They are good conductor of heat and electricity. They are malleable, can be flattened into thin sheets by hammering, and ductile, can be drawn into wires. In contrast, non-metals are located at the top right hand side of the periodic table. In fact, in a horizontal row, the property of elements change from metallic on the left to non-metallic on the right. Non-metals are usually solid or gases at room temperature with low melting and boiling point. Boron and carbon are exceptions. They are poor conductor of heat and electricity. Most non-metallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group. Non-metal metallic character increase as one goes from left to right across the periodic table. The change from metallic to non-metallic character is not abrupt, as shown by the thick zigzag line. Figure 3.3. The elements example silicon, germanium, arsenic, antimony and tellurium. Bordering this line and running diagonally across the periodic table show properties that the characteristics of both metal and non-metals. These elements are called semi-metals or metalloids. 3.7 Periodic trend in properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in element toward the middle of the table, and increases to a maximum in the group 70 non-metal. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of non-metals, say halogens, reactivity decreases down the group. But why do the properties of element follow these trends? And how can we explain periodicity? To answer this question, we must look into the theories of atomic structure and properties of the atom. In these sections, we shall discuss the periodic trend in certain physical and chemical properties and try to explain them in terms of number of electron and energy level. 3.7.1 Trend in physical properties. There are numerous physical properties of elements such as melting and boiling points, heats of fusion and vaporization, energy of atomization, etc., which show periodic variation. However, we shall discuss the periodic trend with respect to atomic and ionic radii, ionization, enthalpy, electron gain, enthalpy and electronegativity. Atomic radius. You can very well imagine that finding the size of an atom is a lot more complicated than measuring the radius of a ball. Do you know why? Firstly, because the size of an atom is very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. In other words, there is no practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atom in the combined state. One practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule and from this value. The covalent radius of the element can be calculated. For example, the bond distance in the chlorine molecule in 198 pm and half distance 99 pm is taken as the atomic radii of chlorine. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystals. For example, the distance between two adjacent copper atoms in solid copper is 256 pm. Hence, the metallic radius of copper is assigned have a value of 128 pm. For simplicity, in this book, we use the term atomic radius to refer to both covalent or metallic radius depending on whether the elements is a non-metal or a metals. Atomic radii can be measured by X-ray or other spectroscopic methods. The atomic radii of a few elements are listed in table 3.6. Two terms are obvious beacon. We can explain these terms in terms of nuclear charge and energy level. The atomic size generally decreases across a period as illustrated in figure 3.4. For the elements of the second period, it is because within the period the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electron to the nucleus within a family vertical column of the periodic table. The atomic radius increases regularly with atomic number as illustrated in figure 3.4b for alkali metal and halogens as we descend the group. The principal quantum number n increases and the valence electrons are further from the nucleus. This happens because the inner energy level are filled with electrons which serve to shield the outer electron from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. Note that the atomic radii of the noble gases are not considered here monoatomic. Their non-bonded radii value are very large. In fact, radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of the other elements. B. Ionic radius. The removal of an electron from an atom results in the formation of a cation, whereas gain of an electron leads to an anion. The ionic radii can be estimated by measuring by distance between cation and anion in ionic crystals. In general, the ionic radii of elements exhibit the same trend as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons While its nuclear charge remains the same, the size of an anion will be larger than that of the parent atom because the addition of one or more electron would result in increased repulsion among the electron and a decrease in effective nuclear charge. For example, the ionic radii of fluoride ion is 136 pm, whereas the atomic radii of fluorine is only 64 pm. On the other hand, the atomic radius of sodium is 186 pm compared to the ionic radius of 95 pm for sodium. When we find some atoms and ions which contain the same number of electrons, we can then isoelectronic species. For example, O2, F, NF and Mg2 plus have the same number of electrons, then their radii would be different because of their different nuclear charge. The cation with the greater positive charge will have a smaller radii because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the large radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ions will expand in size. See, ionization enthalpy, a quantitative measure of the tendency of an element to lose electron, is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom in its ground state. In other words, the first ionization enthalpy for an elements X is the enthalpy change for the reaction depicted in equation 3.1. The ionization enthalpy is expressed in unit of kg mole -1. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction. So in equation 3.2, energy is always required to remove electron from an atom, and hence ionization enthalpy are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positively charged ions than from a neutral atom. In the same way, the third ionization enthalpy will be higher than the second, and so on. The term ionization enthalpy, if not qualified, is taken as the first ionization enthalpy. The first ionization enthalpy of elements having atomic number up to 60 are plotted in 3.5. The periodicity of the graph is cute streaking. You will find maxima at the noble gases which have closed electron shell and very stable electron configurations. On the other hand, minima occur as alkali metals and their low ionization enthalpy can be correlated with their high reactivity. In addition, you will notice two trends. The first ionization enthalpy generally increases as we go across a period and decreases as we descend in a group. These trends are illustrated respectively for the elements of the second period and the first group of the periodic table. You will appreciate that the ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors. First, the attraction of element towards the nucleus, and second, the repulsion of electron from each other. The effective nuclear charge experienced by a valence electron in an atom will be less. The actual charge on the nucleus because of shielding or screening of the valence electron from the nucleus by the intervening co-electrons. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of first electron. As a result, the valence electron experiences a net positive charge which is less than the actual charge of +3. In general, shielding is effective when the orbitals in the inner shell are completely filled. This situation occurs in the case of alkali metals which have single outermost ns electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, successive electrons are added to orbital in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electron does not increase very much to compensate for the increased attraction of the electron to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly, and the ionization enthalpy increases across a period. As we go down a group, the outermost electron being increasingly further from the nucleus, there is an increased shielding of the nuclear charge by the electron in the inner level. In this case, increase in shielding outweighs the increasing nuclear charge, and the removal of the outermost electron requires less energy down a group. From figure 3.6a, you will also notice that the first ionization enthalpy of boron is slightly less than that of beryllium, even though a former has a greater nuclear charge. When we consider the same principal quantum level and s electron is attracted to the nucleus more than a p electron in beryllium, the electron removed during the ionization in an s block, whereas the electron removed during ionization of boron is a p electron. The penetration of a 2s electron to the nucleus is more than that of a 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electron than the 2s electron of beryllium. Therefore, it is easier to remove the 2p electron from the boron compared to the removal of 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the smaller first ionization enthalpy of oxygen compared to nitrogen. This arises because in the nitrogen atom, 3 2p electrons reside in different atomic orbital, hence rule, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron repulsion. Consequently, it is easier to remove the 4 2p electron from oxygen than it is to remove one of the 3 2p electron from the nitrogen. The electron gain enthalpy. When an electron is added to a neutral gaseous atom to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion, as represented by equation 3.3. Depending on the elements, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 element, the halogens, have very high negative electron gain enthalpies because they can attain stable noble gas electronic configuration by picking up an electron. On the other hand, noble gas have large positive electrons gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpy have large negative value toward the upper right of the periodic table preceding the noble gases. The variation in electron gain enthalpy of element is less systematic for the ionization enthalpies. As a general rule, electron gain enthalpy becomes more negative with increase in the atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average will be closer to the positively charged nucleus. We should also accept electron gain enthalpy to become less negative as we go down the group, because the size of the atom increases and the added electron will be further from the nucleus. This is generally the case. Table 3.7. However, electron gain enthalpy of O or F is less negative than that of the succeeding element. This is because when an electron is added to O or F, the added electron goes to the smaller n equal to 2 quantum level and suffers significant repulsion from the other electron present in this level. For the n equal to 3 quantum level, the added electron occupy a larger region of space and the electron repulsion is much less. Electronegativity, a qualitative measure of the ability of an atom in a chemical compound to attract shared electron to itself, is called electronegativity. Unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. However, a number of numerical scale of electronegativity of elements with Pauling scale, Mulliken, Jeffrey scale, and Red-Roscoe scale have been developed. The one which is the most widely used is the Pauling scale. Linus Pauling, an American scientist in 1922, assigned arbitrarily in value of 4.0 to fluorine, the elements considered to have the greatest ability to attract electrons. Approximate value for the electronegativity of a few elements are given in table 3.8a. The electronegativity of any given element is not constant. It varies depending on the element to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together, a relationship that you will explore later. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and it decreases down a group, say from fluorine to arsenic. In the periodic table, how can this trend be explained? Can the electronegativity be related to atomic radii, which tend to decrease across each period from left to right but increases down each group? The attraction between the outer or valence electron and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases on the same account. Electronegativity values decrease with the increases in the atomic radii down a group. The trend is similar to that of ionization enthalpy. Knowing the relationship between electronegativity and atomic radius, can you now visualize the relationship between electronegativity and non-metallic properties? Non-metallic elements have a strong tendency to gain electron. Therefore, electronegativity is directly related to that non-metallic properties of electron elements. It can be further extended to say that the electronegativity is inversely related to the metallic properties of elements. Thus, the increase in electronegativity across a period is accompanied by an increase in non-metallic properties of elements. Similarly, the decrease in electronegativity down a group of accompanied by a decrease in non-metallic properties or increase in metallic properties of elements. All these properties chains are summarized. 3.7.2 Periodic trend in chemical properties. Most of the trend in chemical properties of elements such as diagonal relationship in inert pair effect of length noise contraction etc. will be dealt with along the discussion of each group in later units. In this section, we shall study the periodicity of the valence states shown by elements and the anomalous properties of the second period element from lithium to fluorine. Periodicity of valence or oxidation states. The valence of the most characteristic property of the element can be understood in terms of their electronic configuration. The valence of representative element is usually through not necessarily equal to the number of electrons in the outermost orbitals and or not or equal to 8 minus the number of outermost electrons as shown below. Nowadays, the term oxidation states is frequently used for valence. Consider the two oxygen containing compounds OF2 and N2O. The order of electronegativity of the three elements involves if this compound is F or in each of the atom of fluorine without electronic configuration 2s2p5 share one electron with oxygen in the OF2 molecules. Being highest electronegative elements, fluorine is given oxidation state 1 minus 1. Since there are two fluorine atoms in this molecule, oxygen without electronic configuration 2s square 2s2 2p4 share 2 electron with fluorine atom and thereby exhibit oxidation state plus 2 in Na2O. Oxygen being more electronegative accept 2 electron 1 from each of the 2 sodium atom and thus so oxidation state minus 2. On the other hand, sodium with electronic configuration 3s1 loses one electron to oxygen and is given oxidation state plus 1. Thus, the oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atom in the molecule. Some periodic trend observed in the valence of elements, hydrides and oxides are shown 3.9 table. Other such periodic trends which occur in the chemical behavior of the elements are discussed elsewhere in this book. There are many elements which exhibit variable valence. This is particularly characteristic of transition elements and actinoids, which we shall study later. Anomalous properties of second period elements. The first element of each of the group 1 lithium and second beryllium and groups 13 and 17 boron to fluorine differ in many respects from The other members of their respective group, for example, lithium, unlike other alkaline metal, and beryllium, unlike other alkaline earth metal, form compound with pronounced covalent character. The other membrane of these group predominantly form ionic compound. In fact, the behavior of lithium and beryllium is more similar with the second element of the flowing group, magnesium and aluminium respectively. This sort of similarity is commonly referred to as a diagonal relationship in the periodic properties. What are the reasons for the different chemical behavior of the first member of a group of elements in the S and compared to that of the subsequent members in the same group? The anomalous behavior is attributed to their small size, large size, radius ratio, and high electronegativity of the elements. In addition, the first member of group has only 4 valence orbital, 2s and 2p, available for bonding, whereas the second member of the group have 9 valence orbital. As a consequence of this, the maximum covalency of the first member of each group is 4. Example, boron can only form Va4-, whereas the other members of the group can expand at their valence shell to accommodate more than 4 pair of electrons. Furthermore, the first member of p block element display a greater ability to form p pi minus p pi multiple bonds to itself and to other consequent pair elements compared to subsequent member of same group. 3.7.3 Periodic trend and chemical reactivity. We have observed the periodic trend in certain fundamental properties such as atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and valence. We know by now that the periodicity is related to electronic configuration, that is, all chemical and physical properties are a manifestation of the electronic configuration of element. We shall now try to explore relationship between these fundamental properties of element with their chemical reactivity. The atomic and ionic radii, as we know, generally decrease in a period from left to right. As a consequence, the ionization enthalpy generally increase, with some exception as outlined in section 3.7.1a. Electron gain enthalpies become more negative across a period. In other words, the ionization enthalpy of the extreme left side in a period is the least, and the electron gain enthalpy of the element on the extreme right is highest negative. This results into high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left among alkali metals is exhibited by the loss of an electron, leading to the formation of a cation, and at the extreme right among halogens, so by the gain of an electron, forming an anion. This property can be related with the reducing and oxidizing behavior of the elements, which you will learn later. However, here it can be directly related to the metallic and non-metallic character of elements. Thus, the metallic character of an element, which is highest at the extremely left, decreases, and the non-metallic character increases while moving from left to right across the period. The chemical reactivity of an element can be based so by its reaction with oxygen and halogens. Here we shall consider the reaction of the elements with oxygen only. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the elements on the extreme left is the most basic, whereas that formed by the element on extreme right is the most acidic. Oxides of element in the center are amphoteric or neutral. Amphoteric oxide behave as acidic with bases and as basic with acids, whereas neutral oxide have no acidic or basic properties. Among transition metallic series, the change in atomic radii is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metal 4F series. The ionization enthalpies are intermediate between those of S and P block. As consequence, they are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionic radii with increase in atomic number generally result in a gradual decrease in ionization enthalpy and a regular decrease, with exception in some third period element as shown in section 3.7.1d. In electron gain enthalpy in the case of main group of elements, thus the metallic character increase down the group and non-metallic character decrease. This trend can be related with their reducing and oxidizing property, which you will learn later in the case of transition element. However, a reverse trend is observed. This can be explained in terms of atomic size and ionization enthalpy. So thank you so much.